Hi guys, I'm Willa Vaughn.
Hi, I'm Anna Jones.
Chris Crow once again at your service. We are the Mathematical Martians, and we are going to be bringing you the next Team Teach lesson. This time it is going to be Module 4, Chapter 11, Transformations, Symmetries, and Tilings. Without further ado, let us jump into the video.
All right. So, Chris, I have a question for you.
Go ahead and ask it.
Can you help me define what rigid motion is?
I can indeed help you define that. It's actually a lot simpler than it sounds. So a rigid motion is basically describing a way that a figure can move in some form or fashion. So it can change positions, it can change its formatting, but it doesn't change its size, or it doesn't grow larger or smaller, because that is the exact opposite of a rigid motion. So, for example, we have this figure right here. We see it starts out with trapezoid on the bottom, square middle, and then two triangles to form the top. And then over here, it has been changed in some way. Now, the question says that the goal was to reflect it over the horizontal line through the center of the square. Now, the goal of this question is to answer, is this a reflection? And if it isn't, what is?
Okay.
So the way I went about figuring this out is I looked at a circle for a reference. And so the reason I did that is because a circle is all the way around 360 degrees. And so I got to thinking, okay, the figure has been moved about halfway instead of going a complete 360. What's half of 360? 180 degrees.
Okay.
And so that is what we call a rotation, where it is literally just twisted on itself to any certain amount. It could be 90, 180, 450, whatever the case may be. And yeah, so they actually performed a rotation instead of a reflection.
Wow, I never knew that it had to do with the degree of it and how it was flipped.
Yeah, I like how you decided to use a circle to show the reflection, to like think of the reflection.
Yeah, I never would have thought that it being flipped 180 degrees had anything to do with it other than 360. That's really neat how you explain that.
Oh yeah, and that's just one of the several different rigid motions that can take place.
Yeah. Huh.
And who of you is among the same intelligence level as me in order to tell us what kind of motion was actually supposed to happen, or how a reflection is supposed to look?
Well, looking at the question, wouldn't it be just similar? Like, look basically exactly the same?
That is the correct answer. So the way a reflection works, which is what the original goal of the question was, it's simply being scooched over in some way. Now, the figure shown is actually what a reflection should look like, but the figure should be reversed. So the triangles actually need to be pointing towards the original figure, because a reflection is not just copying the image and pasting it over. It's actually somewhat flipping it, but not rotationally. What you see there would better be described as a translation.
Okay. Huh. Neat.
Throwing those in there to try and trick you, students.
Yeah, I saw that and I was like, wait a second, that's not quite right.
All right.
So now I actually have a question for Miss Anna. And that would be, where does the line of symmetry need to be placed on a figure?
Okay. So actually, I'm going to steal this question from Anna. Yeah. Sorry, Anna.
Oh, that's okay. You go ahead.
All right. So the line of symmetry, So you can see in this figure, it asks you to show a line of symmetry, but no rotational symmetry. So right here in the middle, you see my red line right here. The line of symmetry is going to be showing where it looks similar. So you have the tops right here, the exact same, and it's being reflected over this line of symmetry. So it just is placed where it's going to show the exact thing over each side. And you can also see it asks about the rotational symmetry. So the rotational symmetry, like on this one, it's not going to have an actual line because it's going to have a point where it's supposed to be. So can anyone tell me why, like where the point would go and why it goes there?
I think the point would go in the center, right?
Okay.
Yeah.
Kind of. So where it's going to go, it's going to be the same thing as the line. It's gonna go like somewhere up here, and where it's gonna go is it's gonna rotate over itself on the line, and so it's gonna be the exact same thing. So wherever the point is that it rotates, it's like the reflection you gave us. It has to rotate that 360 degrees. Well, it's actually going to rotate the 180 degrees, not the 360. So when it rotates the 180, it's going to reflect the exact same image, as opposed to rotating a whole 360 and being the same image.
Okay.
Okay.
Yeah.
Okay.
So it's kind of like it's like the opposite of the reflection that you gave us, Chris.
Okay.
Yeah.
Okay. I think I'm getting this now.
Yeah. Yeah. Instead of not using the 180, you are using the 180.
Gotcha. Okay.
Yeah. And where there is rotational symmetry, there is no reflection symmetry. You cannot have both. You can't have it reflect on a line as you reflect on a point. It just doesn't work that way.
All right. That's good to know.
Yeah, the symmetry, you think the symmetry would be easy, but it's got a little tricks in there for you.
Yeah.
They're trying to dupe us into doing wrong things.
Exactly, yeah. All right. Anna, can I ask you a question?
Yes, ma'am.
All right. What is a vertex figure exactly?
So as you can probably already tell from these figures that are here, that a vertex figure is a shape inside of another shape that takes one of the shape's vertices. So this could really be any shape.
Okay.
It could be a triangle, square, rectangle, anything. As long as it's connected to one of its vertices and makes a shape within, it would be considered a vertex figure.
Okay.
All right. And here we have this figure that Myra cut out. She cut out a regular pentagon, hexagon, and octagon. And it seems to her that it forms a vertex figure. And I don't think this actually makes a vertex figure, because in Myra's version, the interior angles is 108 degrees, 120 degrees, and 135 degrees, which adds up to 363 degrees. So it doesn't equal that full 360.
Okay.
Like a normal vertex figure would. So her figure has some overlapping in it.
Huh.
Yeah.
That's funny. All of our things have to do with degrees, and you wouldn't think that any of these had to do with like angle degrees.
Right.
Huh.
No, it's kind of deceptive that way.
Yeah. There's a lot more to shapes than just shapes. You gotta get those interior angles just right.
All right.
Okay. Oh.
Alrighty.
So, Chris, I have a question for you.
Ask away.
What congruence property is applicable to this question?
That is a very good question, Anna. So looking at this particular question, we see the figure shown to demonstrate why, use the figure shown to demonstrate why triangle QPT is equal to triangle SPT, how angle QPT is equal to angle SPT, how triangle QPV is equal to triangle SPV, and how angle QVP is a right angle. So in this particular instance, there are actually going to be a couple different congruence situations that we have to deal with. There's side angle side, there's side side side, there's side angles, there's side angle angle. This particular one, most of these can actually be figured out by looking at them through a reflective manner. You don't even have to use the congruence rules to figure this one out. So if you take the line that I've put through the figure, you can actually see that the reason all that A, B, and C are true is because every single triangle is a reflection of the one that it's asking why it's equal to. So we see that triangle QPT is equal to triangle SPT because they are reflections of each other. They're opposite but equals. And in this particular instance, the side angle congruence would actually fit pretty well with them.
Okay.
All right.
So you just really need to know that they reflect each other.
Yes.
Yeah,
To
kind of.
make it to simplify it to a
Yeah.
certain extent.
Okay.
Yeah.
It's good to know.
Oh yeah, it can be quote unquote dumbed down for people that have a hard time forgetting some of the different congruence rules.
Hey, I'll take the
Yeah.
dumbed down version.
Yeah, it makes it easier.
Yeah.
Now, the next question that I have is for a Miss Willa Vaughn.
Yes, sir.
So my question is directly related to question 5 in that I'm trying to figure out how and why the triangle / angle NOQ is formed within the grand figure.
Okay, so that's a really great question. So what we have, so I'm going to use the whole question to answer this. We have angle NOQ right over here, and I'm actually going to move our faces real quick so we can see it better. So you can see as soon as the angle NOQ is formed, you have a triangle that's formed. Angle POQ. So this triangle, because triangles are 180 degrees, that's what you use as your measurement. And so now you can find you find the interior angles. And so you would be taking, so NOQ is going to hit 2 points of your pentagram. And so you take the angles 144 degrees minus 120 degrees, and that's going to equal 24 degrees. So that's kind of the relationship between the penta, PQR, and then that's going to create an OQ because it's going to automatically form that triangle and then hit 2 points on your pentagram.
Wow.
Okay.
You explained that really well.
Thanks.
That's
This
a
one.
wonderful explanation and
Yeah.
greatly opened my eyes to how that was actually supposed to be done.
All right, this looks really complicated.
It does, yeah. There's like a whole transition into these. But once you kind of get those stages in and you see where NOQ hits in your shapes, makes it a little easier.
Yeah.
It does make it kind of simplified whenever you had it explained as well as you do.
Well, thank you. All right. So, Anna, why do we have to cross multiply in this problem?
So as we can see here, that cross multiplication is usually found to find a value. We usually use x as the value, but it can be anything. So we would cross multiply to stick that value, whatever value it is, to another number and figure it from there. Okay.
Okay.
And so like in this question, by holding a ruler 2 feet in front of her eyes as illustrated, I can't see her name. Jenny sees that the top and bottom points of vertical cliff face line up with the marks separated by 1.5 on the ruler. Jenny is about a quarter mile away from the cliff, so what we need to figure out is what is the approximate height of the cliff. So we can recall that a mile is 5,280 feet, which is going to help us greatly. So 1 mile divided by 4, so that's 5,280 feet divided by 4. That equals 1,320 feet. And then we're going to use that 1.5 inches that we got on the ruler and convert that to feet, because we need everything to be in the same unit of measure. So that's going to be 0.125 feet. And then we're going to cross multiply to find the height of the cliff. So 2 feet divided by 1,320 feet times the 0.125 feet divided by the height. So that's going to be our x value. Here I have it written as h. And then we continue our cross multiplication. It's going to be 2 feet times h. So that's going to be 2h feet. So that value is now connected to our 2 feet. And then we have 1,320 feet times 0.125 feet. And we simplify to 2h feet equals 165 feet. And then we're going to divide those in half to get the h by itself. Or we're going to divide it by 2 to get the h by itself, being that there's a 2 connected to the h. And then h will equal 82.5 feet.
Okay.
Wow. Very
Yeah.
impressive.
I didn't.
This was definitely the one I had the most trouble with, so seeing it laid out like that is helpful.
Yeah. Yeah, that math is very clearly put. Really like how we can follow along very easily with that.
I know who I'd want as my math teacher.
Oh, I don't know about that.
All right. Right.
And I think that's our last lesson.
Yeah, I think we've reached the end, guys.
Alrighty. Well, thank you guys so much for joining us for our final team teach. It is sad to go, but we hope that we managed to give you guys a little bit more insight into the rigid motions, into tilings, into symmetries. Hope we give you guys a bit more insight on that on the way out. Thank you so much for watching us. I'm Chris Crow.
Willa Vaughn.
And Anna Jones. Bye.
Bye.
Bye.